Okay, so I wanted to get you started by helping you set up problems involving uniform circular motion. So there's a series of steps that you want to follow that'll help you be successful with these. So first step, just like when we were doing forces before, is to identify your system. What mass are you interested that is moving in a circle? And just identify it. Second part, free body diagram, just like we start all the time, but there's a couple of different steps that you should consider that are a little bit different than what we've done before. So first is think about, are we talking about a horizontal or vertical circle? This may affect how you draw your free body diagram. There may be several versions of it that you want to include. Is gravity going to be a factor? Is that something that's contributing to the circular motion? All right, now you want to identify the forces pointing directly towards the center or directly away from the center. And then I think it's just a great idea to help you get started by adding a circle to your free body diagram so you can get a sense of which forces are pointing towards the center and which ones might be pointing directly away from the center. And as we do a couple of example problems, you'll kind of see why I think that's a really great idea. All right, the sign conventions. So, and this is just something that I do. You may not see it in all textbooks, but I find it's a great way to solve problems, is just to have the general sign convention that towards the center is going to be the positive direction, and then away from the center will be the negative direction. So remind yourself, kind of commit these to memory, these steps, and I'm sure you'll be successful with solving problems with things moving in a circle. All right, so let's go to our first example here. So we have a driver car of mass m1 goes over a hill of radius r with a constant speed v. What is the apparent weight of the driver at the top of the hill? All right, so a little sketch of my system is probably in order, and this is probably an exaggerated hill. So we're just saying that this hill actually has a perfectly circular radius, which of course may not be true, but we're just going to consider what's happening at the top of the hill, where the car is, and then our passenger hanging out on the top there. All right, so free body diagram of just the passenger, and I'm going to include a circle as my point of reference. So I got the person here. He's going to have a normal force directed upward from the car on the passenger, and then I'm going to have a weight vector going down. Now, in the past, when we have looked at the normal force versus the weight vector, and it looks like a horizontal situation, we've always said that these two are going to be equal to each other. And that is true. If you are traveling on a level, flat road, then your normal force would be equal to your weight vector. But now we're moving in a circle. So we know that we are accelerating towards the center. So that tells you right away that my weight vector must be greater than my normal force. Okay? And this idea of apparent weight really is asking you, what is your normal force? The normal force is our sensation of weight. So this is how we set it up. All right, so we've identified our free body diagram. Our sign conventions are going to be towards the center as positive. Now, if I just drew my free body diagram without the reference circle, some of these problems where you're actually at the bottom of a hill, say like a Ferris wheel type problem, well then, if this was a Ferris wheel, my normal force would be pointing towards the center, and that would be the positive direction. So it's really important to include that reference circle. All right, so we'll start out with our net force equation. Sum of the forces is equal to mass times acceleration, Newton's second law. We know that our centripetal force is going to be equal to the mass times our centripetal acceleration. Our centripetal force here, these are the force or forces acting directly towards the center or directly away from the center. In this case, it's going to be our weight minus our normal force is equal to our mass, m1, which is the mass of the person. Centripetal acceleration is defined as v squared over r. So that is our net force equation that we've developed, and now we can solve for the apparent weight by simply solving for the normal force. And if we had numbers, you just plug them in. All right, so that's kind of example problem number one. Second problem, so that was an example of a vertical circle. Now we'll look at a horizontal circle where you have a car of mass m turns a corner on a level road. Cross out that D, that's a typo. The coefficient of friction of the tires on the road is mu. Determine the maximum constant speed of the car can drive before starting to spin out. Well, this is really recognizing, and this is a little bit different type problem. What is holding the car moving in a circle? Well, to prevent you from sliding out, it's really static friction that is acting towards the center of the circle that is preventing your car from sliding out. So if we look at kind of a head-on view of my car, and actually let's make it head-on so the tires are looking like that. And here's the windshield, and I'm driving out of the page and kind of coming out of the page and coming back in, so I'm taking my turn like that. What's preventing it from sliding out is actually a static frictional force that is keeping you in the circle. So here is an interesting version of, sometimes it might help to look at a top-down view of what's going on here. So again, if I look at my circle, and let's say he's taking a curve, but I'll do the whole circle. Here's my car. It is going to be a static frictional force that is keeping you from sliding out. So once, if you have bad tires, icy road, there's less friction, then you're going to start to spin out and head out tangent to the circle. All right, so that's one version of our free body diagram. But since we're talking about static friction, it kind of brings to mind that we know that the maximum value of our static friction is going to be equal to mu s times the normal force, and the normal force is going to be that weight vector. So it might be an advantage to kind of look at a side view of our free body diagram as well. So if this is our car right here, M1, we know it has a static friction ending towards the center of the circle, and I'll call that the center of the circle. We're going to have a normal force upward and a weight vector down. In this case, because it's moving in a level, flat road, then we know that the normal force and the weight vector are going to be the same in this case. So this can be a little bit confusing, but again, it's about the context of the problem and just conceptually reasoning your way through it. Okay, so our static frictional force, let's do sum of the forces, is equal to our mass times our acceleration. Static frictional force is going to be equal to big M. Our centripetal acceleration is v squared over r. And we said it was a, I didn't give you the radius of the road. So let's say the radius of the road is big R. We'll just call it big R. And we want to solve for the maximum constant speed the car can drive before it just starts to spin out. So again, we're looking at this maximum value of the static frictional force. I want to solve for Vs. If we're not given this force of static friction, but we can solve for it, we know that it's equal to mu s times the normal force is equal to mv squared over r. And now we can simply substitute in if we had actual number values, and we can solve for that maximum constant speed. So this should help you get set up, at least for the first few problems. A couple of them I haven't really set up for you, but just think your way through it, follow the steps, and you should have good success with the first 4 problems.